This is our first clicker quiz for the day. Which diagram best represents the chemical potential as a function of temperature at constant pressure for a pure substance? If you remember from last chapter, the slope of these curves depends on the negative entropy. So therefore, gases, since they have a higher entropy than liquids, are going to have a more negative slope. And since the entropy is always positive, the slopes will always be negative. So however these curves are arranged, they need to both be sloping downwards, and the vapor slope needs to be more negative than the liquid slope. So the only correct answer is this one right here. Let's talk about calculating the chemical potential of a particular substance in a solution or a mixture. I want to make the comment that so far we've been able to use the delta GM, or the molar Gibbs free energy. And the reason we've been able to do that is because it equals the chemical potential for a pure substance. Unfortunately, in this chapter, we can no longer make that assumption because we're dealing with mixtures here and solutions. And we will see that this does not apply for mixtures because we're going to have a Gibbs free energy of mixing. And so that one is going to be covered in the next slide. So now we have to switch over to using this chemical potential only. All right. So if we have component I in a mixture, then we're going to be considering the chemical potential of substance I. And this is going to allow us to take the step towards getting equilibrium constants for the given components within the mixture. Okay, so since the vapor and liquid of component I are coexisting, we can say that the chemical potential of component I within the solution is going to be equal to the chemical potential of component I within the vapor. And we're assuming that the vapor is described by an ideal gas. And that's a fairly valid assumption for just about everything that we'll need to consider in this course. And that's going to be really convenient for us because we already learned that the chemical potential of anything in the vapor phase or in the gas phase, and we can say for our particular component I, is equal to the chemical potential of that component in the standard state plus RT log Pi over P naught. This is indistinguishable from what we covered in chapter 6 with regards to ideal gases. This is the partial pressure of the ideal gas for component I in the vapor above the solution. So, first let's imagine a system of pure I, again in a tank, say, and the vapor is up there above the liquid phase. Then we would write, we've got the vapor chemical potential, and remember the star represents the pure substance. This is going to equal the chemical potential of the substance in the standard state plus RT log whatever the vapor pressure would be for that tank of pure substance, P naught, like so. Okay? So another way to write this is that the chemical potential in the standard state is just mu I star minus RT log P star I P naught. And we're going to be able to use this directly to plug in right up there. So let's do that now. The chemical potential for substance I in the solution is equal to the chemical potential of the substance in the vapor, because they are coexisting with each other. This just equals the chemical potential of the pure substance log Pi star over P naught plus, oops, this is supposed to be a negative here, and then plus RT log Pi P naught, like so, okay? And then we can just pull out an RT for these two expressions here, and we get mu I star plus RT log Pi P naught minus log P star P naught. And we can just use the rules of logland to combine those two logs. The chemical potential of substance I in the solution, chemical potential of the pure substance plus RT log Pi P naught multiplied times P naught P star, because remember, when you subtract two logs, that is a division in logland. So this just equals mu I star plus RT log Pi Pi star. Okay? So now we can use Raoult's law, which remember is just the partial pressure of component I in the mixture is the mole fraction times what the vapor pressure of the pure substance would be. And that's just equivalent to saying that the partial pressure in the mixture, vapor pressure of the pure substance, equals that mole fraction. And so we can just plug that right in there. So that just means that mu I for our solution is the chemical potential of the pure substance plus RT log mole fraction for ideal solutions. So I know that was sort of a long process, and you might be wondering, wow, like, what do I even use this knowledge for? The whole point of this was just to show you where this expression came from. And it's most likely that you will be using that expression for your homework and not necessarily these individual steps, but I just wanted to walk you through this thought process of where it comes from. I'm trying to help get you used to how to think about these chemical potentials. The key takeaways that I want you to remember is that when two substances are coexisting, their chemical potentials are equal. That's a really important thing to keep in mind. The other things I want you to keep in mind and take away from all of this was that we're relating everything to the pure state, because that's a nice sort of launching point for understanding mixtures. That was what I also wanted you to take away. That we're using the assumption that the vapors above the mixture are ideal gases, and that we're using Raoult's law to relate the chemical potential to mole fractions.